Hey everyone, welcome to another video. I was reading this article that is in front of you, and I decided to make this video to not only showcase this new open source tool for high content mitochondria analysis, but also to show a similar project that I've been working on, uh, which also utilizes the similar feature extraction profile as this one. So I will go ahead and demo these two projects in this video. So if you are interested in mitochondria analysis, you would probably know that understanding mitochondrial fragmentation and networks is quite a challenging task. Now, these authors of this paper, came up with a clever way. Here they are showing in panel I and J how they utilize something called the spot and the ridge texture of the mitochondria to understand whether fragmentation is happening or whether the networks are leaning towards connectivity. Okay, but they also presented two pipelines. One is for their proprietary platform. The other one they made open source. So by open source, I mean they utilized Python and Napari interface to give us researchers a tool to utilize for mitochondrial segmentation, cell segmentation, and nuclear segmentation. Okay, so I will go ahead and show you what this GitHub repo is. So here it's called Napari Mito HCS, and you can read how they describe it, and then learn how to install it in your own Anaconda environment. It's fairly easy to use, so I'll actually go ahead and bring that up and do a quick demo. So once you install all the packages that they have listed in their libraries, you would be able to open Napari like this, and then go to plugins, and then open their MitoHC plugin. I'm going to utilize their own sample images. Here, for example, the mitochondria KO. This is the MitoFusion 2 knockout cell line. As you can see, these are the cells, and these are the mitochondria channel, and this is the DAPI stain. On the right here, the panel shows different nuclear images. You have to actually select the image that you want to utilize. Make sure you are utilizing multi-channel images with this. And then basically it's just point and click here, and then this is for segmenting cells. And the next one is the mitochondria. So I'll pick the mito image and utilize this using, let's say, 6,000. So if I block out all the other ones, okay, and here we can see this is a thresholding based approach. It has all the limitations that any other threshold method has. Right, so you can see that it's doing okay job of segmenting mitochondria, but some of the lighter intensity mitochondria are decreasing. They're not being quantified in this analysis. And here, for example, it's merging. Okay, anyways, so the platform that that researchers have provided us, it could be useful for some of you who do single cell imaging, and it could be a nice way to basically streamline your analysis. And then following that, you can pick the feature extraction profile. So here I'll pick the mitochondria to do the feature extraction, calculate features, and then over here on the left, you can pick the type of objects you want to see. So here, for example, these are the spots that the researchers utilized in their analysis. So they're basically taking the comparison of spot and the ridge feature to understand whether there's more fragmentation happening or more networking going on. By taking the ratio of these two features, one can figure out, based on the texture, whether mitochondrial networks are leaning more towards fragmentation or not, which I think they did a fairly nice job Obviously, the threshold-based approaches have the inherent limitations of being very intensity-driven, and therefore you can lose some of the features or some of the low-intensity mitochondria in this approach. Now, let me show you another aspect that I was working on separately from this, and I'll put that on GitHub as well. And you guys, if you find that to be useful, you guys can utilize it. So here's the pipeline for the mitochondria analysis that I was creating. Um, and this was specifically for Z projections of mitochondria. So if you do any kind of stacks, if you take stacks of images, Z stack images, then you know how to probably do a Z projection of mitochondria. Now in this particular project, I wanted to utilize Napari and their Segment Anything plugin. Segment Anything models have been around since I think 2022, and don't quote me on that, but they've been around for quite a bit, and they allow you to point and click to extract certain features. It's an AI assisted segmentation, basically. Right? I have all of the instructions on how to install it. If you have a NVIDIA GPU accelerated segmentation can obviously help, but if not, then you can obviously use the CPU PyTorch and the Torch installation for that. Okay, so without further ado, let me go ahead and discuss some of the features that one can extract using this project. The standard basic region properties of the mitochondria can be extracted. The image intensity features can be extracted. And I have few extended morphology features that I personally extract for my own images. And those include perimeter area ratio, and this is a proxy for surface area to volume ratio that I often do for my 3D image segmentations. But here it's being utilized to indicate the complexity of the mitochondria morphology. And let me show you what I mean. I'm going to download this and open this. So convexity, concavity, these concepts have been around for a while, as well as the aspect ratio and the form factor. But the perimeter over area ratio, I believe this is not very standard, and this is partly the novelty of this project, is the more complex the shape of a mitochondria is, the more P over A ratio will be. Okay, so if you take a shape like this, which is a zigzag shape to the mitochondria, elongated but zigzag shape of the perimeter, and then you try to fit an approximated area, like let's say an oval shape to that area to approximate the area of that shape, what you will find is that the perimeter will be larger than the area that can be bounded by a bounding box or bounding circle or some kind of a known object. Okay, so the P over A ratio will be extremely large for complicated shapes. So in other words, it reflects how complicated the shape of the underlying object is when you have a higher P over A ratio. So for some projects, that can be very, very useful. Okay, so let me start this one and I'll demo this. Okay, so let's go back here. So in the terminal, you will see that it will tell you what is happening. So here, for example, the Napari is opening. The Napari use segment anything, use segment anything or segment cells and objects by yourself. Then rename the layers to cells and masks, cells underscore masks, and objects, which are mitochondria. You have to label the segmentation layer as objects underscore mask. It's actually quite easy, and I will show that as I'm doing this. So over here on the left, this button is for creating a new layer. If you double click on this, you can rename it. I'm going to rename it cell underscore masks. And if I pick the pen, I can go ahead and draw the mask on top of where my cell is. Okay, so that's my cell, for example. But I can also utilize the segment anything model with this and load in an AI model to help me segment. So I have already activated my model. I'm going to change this to be point size of 10. I'm going to use my middle mouse button to click and choose the cells that are here. Now, if you will notice that it has also picked these other areas of high intensity, which I don't want, so I'll pick the eraser and just come back here and erase those out. Okay, so that's my cell segmentation. I can utilize the same model for segmenting the mitochondria that are inside, but I also want to show you how you can utilize this with a manual approach. And before I start segmenting my mitochondria, I will go ahead and rename the layer to object underscore masks. And if I come back here and scroll up, my layers are named cell underscore masks and object underscore masks. So my naming convention is correct. I don't have to worry about that. I'm going to change the color here and decrease the size. Use the pen to go ahead and just mark the areas where my mitochondria are present. Now I'm going to do a very crude segmentation using this pen. So these are my two masked layers. Here is the mitochondria and the cell is in the brown. And so once I've finished this segmentation, I can come back here and come back to my terminal and press enter. And then this message will pop up saying the analysis is complete and the CSV has been saved. So the way the CSV is getting saved is back here in the same folder where I'm running my script from. So within the script, within the CSV, the script is saving many different things, including the cell number. So I had 3 cells, and you will find that there are 3 cell IDs. Depending on how you color them or how you segment them, it's going to label the cell number as different. Okay, and then the object is the mitochondria. Each mitochondria associated with that cell is present here also. The perimeter area ratio for most of the mitochondria are it should be all of them present there. The branch numbers, how many branches it has detected, are also present. The total branch length is present as well. This is just the sum of all of the branches. So for higher branch counts, there will be higher total branch length. Then the average branch length is also presented here, and the number of junctions. Okay, so overall, this is just a small video I wanted to make, and I will leave the link to both of the repositories down below. For my Python project, you can find that on my GitHub repo. For this paper's Python project, I will find their link and post it in the video description below. All right, so thank you so much. Bye bye.